As our senior project, we implement the privacy-preserving sorting algorithm with three-party computation. I'm Orhun Görkem.
My name is Safa Burak Altunel.
And I'm İsmail Ata İnan.
To explain our algorithm, we need to first mention arithmetic secret sharing. Arithmetic secret sharing's aim is doing calculations with multiple servers, but not sharing the whole data with any of the servers because we don't trust them. And for a brief example, I can explain addition in arithmetic secret sharing. Suppose I want to add a plus b, and I split a into two shares, a1 and a2, and also for b, I split to the shares. And then a1 and b1 are shared to server 1, and a2 and b2 are shared to server 2. And then each server does this addition locally, and their sums are then added to each other, and a plus b equals c is calculated, and none of the servers know about a or b. This can also be done with multiplication with a more complex structure, but Sicilia is a framework that does such kind of operations with multiple servers. And like addition, multiplication, and modular conversion, most significant bits are calculated with multiple servers securely. And our contribution to Cecilia framework is implement the sorting algorithm. And the idea is the following. Suppose we have an input array like this, and shares from the array are shared with servers. So the servers don't know the original array, and there are a couple of operations done in this procedure. Now they are black box, but we will explain it. And then they output their results like this. And when the results are reconstructed, we obtain the sorted version of the input array. And we did this implementation. And now Ata will explain about the procedures we do technically.
And now let's look at the overall sorting procedure that we used. Actually, in our algorithm, we initialize a q variable as 1 and copy the input array to an array called result. And at each step, we get the most significant bits of the variables in the array and store them in an array called MSP array. And we give this MSP array to a procedure called gambit perm to get the permutation that stores this bit array. And after that, we use a procedure called apply perm to get the sorted version of this bit array. And we repeat this algorithm 64 times because we use 64-bit numbers. And after sorting all 64 bits like a radix sort, we get the sorted version of the input array. So let's look at our procedures in more detail. Gambit perm is an algorithm to generate the permutations that sorts a single bit array. It uses some complex structures that we implemented and explained in the poster as you see. And this gambit perm actually gives us the inverse of the permutation that stores this array. And after that, we use apply perm algorithm to apply this permutation to our bit array securely. And in this apply perm, we actually use two proxy servers, and each proxy server has a share of P and V, denoting the permutation and input array. And they are just shared between them using arithmetic sharing. And P is just a random permutation that both servers share in common. S0, our first proxy server, generates a random array R and adds it to V0, storing it in V0. And after that, both servers calculates P and PV and sends it to helper server. Then helper server just reconstructed arithmetic shared these variables, PP and PV. And after that, using them, it calculates P to the -1 V. And using arithmetic sharing again, it just splits them into both proxy servers. After that, S0 picks a random variable X, and R is multiplied with X and take it mode N, where N is a prime number 2 to the power 61 - 1. After that, it calculates PR and sends it to helper server again. And helper server, using the information earlier, the PP, it calculates P to the minus 1R and sends it to S1. And S1 needs to eliminate the effects of the random variables R and X. So it just P to the minus 1R is multiplied with the modular inverse of X in mod N to eliminate the effect of X. And after that, P to the minus 1 V is subtracted with P to the minus 1R to eliminate the effect of R. And now they have the arithmetic shares of P to the minus 1V. When we reconstruct them, we get the sorted version of the input array V. It's just a bit array. And now Safa is going to talk about our results in this project.
Okay, so we tested our framework with different input sizes like 100, 1000, 10,000, and 100,000. We also added some round trip times to our servers to simulate a real world example. So we draw two figures. In figure one, we compared our input size with the bytes used in communication in our algorithm. As you can see, the array size and bytes have a linear correlation. So we can say that our algorithm is linear in terms of space complexity. Here in figure one, we are seeing 6 lines. These lines are bytes sent and received from proxy 1, proxy 2, and helper proxy. And these bytes are close to each other. So this is our first figure. In the second figure, we looked at our overall time to run the algorithm with different input sizes and different round trip times. When we take round trip time constant, we can see that increase in our input size has a linear effect on the overall time complexity of our algorithm. And you can see that the overall running time is increasing from bottom left to top right. But we can see that, for example, when we increase our round trip time from 0 to 20, in the input of size of 100, we see a significant change of our running time. So we can see that round trip time has a significant effect on our algorithm. So yeah, that's all. Also, we want to thank Fatih Alagöz, Beta Akün, and Ali Burak İnan for their contribution for the project and for providing Cecilia source code. Thank you, everyone.
Thank you.